recording now. So I was telling that the current coming from the supply to the transformer which is not connected to the load. So the current from the supply creates the flux, but as soon as you connect the load to the transformer on the secondary side, this load starts drawing a current. So there's a current in the secondary circuit, and that flows through the secondary coil, and this current, it creates an opposite flux into the core that tends to decrease the initial flux. But because the flux cannot be decreased, it has to remain the same. The supply side will send out more current, extra current, to compensate for the loss of flux, or the extra current coming from the supply would provide exactly the same amount of magnetomotive force that this current in the secondary circuit, the load circuit, has created. Okay? So the magnetomotive force, as you know, is I times N. Right? And so magnetomotive force created by the load is I2 times N2, if the number of turns in the secondary coil is N2, and the current in the secondary circuit is I2. So I2 times N2 is the magnetomotive force from the secondary side, from the load side. To compensate this, generator has to give an extra I1 dash, let's say I1 prime current. So this I1 prime times N1 should be equal to I2 times N2, isn't it? And so the flux would remain the same. So let's begin. Let me share my screen. Go full screen. There we are. So essentially, I was talking about this I2 current, which creates opposite flux. And to compensate this, maintain E1, generator produces extra current. Let's say this is I1 prime. So it'll be this much. Now, the thing is, the flux has to remain unchanged. That's the condition. Now, that's true actually. Flux in the core, it will always be same, irrespective of the load side. Be it any load, the flux will always be the same. Now, when you have a load, and specifically if you have a resistive load, so the load would have some inductive effect. So I can presume this current I2, which is in the second circuit, to be lagging behind the voltage, isn't it? That's an inductive load. Most of the loads, they are inductive. If it was a capacitive load, story would be altogether different. Okay, but normally it's an inductive load, and so I can say that the current is lagging the voltage, because I remember the phrase "early the Iceman." Okay, and to compensate this, the generator has to produce an equal and opposite kind of current, which is I1 prime. Okay, this is an extra current. Initially, it was providing IE, and now it is also providing IE prime. So what does it mean? That the total current that comes from the generator is now this plus this, or in other words, it's this now. Okay. And so what will be the power factor in the primary side? It's going to be this much. So this is how we make the phasor diagrams. The flux into the core is lagging behind the generator voltage by 90 degrees. the induced voltages in primary and secondary lags 90 degrees to this phi. Okay. And the excitation current from the generator in the beginning, when there was no load, has to be in phase with phi, because this guy is creating this. This is not always true. This is not always true, because you know that there is always a kind of hysteresis. And that makes this, if this is your excitation, HE or N times I over here. If this is your excitation and this is your flux generated, there's always a lag, isn't it? There's always a lag. But still, ignoring that hysteresis effect, we can say that they're in phase. And then this is an extra current, which has to be opposite to this I2 in secondary circuit. So this is an extra current coming from the generator, and this is the total current. Fine. Okay. This is magnetomotive force 1, and this is 2. This is because of the secondary, and so these have to be the same. Further. Now, because the phase is not 90 degree now, initially it was 90, IE, and the voltage. So there was no power transmitted, but because now the thing has changed, scene has changed, and they have less than 90 degree, and so there will be some transfer of energy from the primary. Now, rate of energy generated to the primary and rate of generated transfer to the secondary should be the same, right? And so I can say that, roughly speaking, this I1V1 should be equal to I2V2, or I1E1 should be equal to I2E2. And this is something you have done it long back, and you know it already, that the currents, the two circuits, will depend on the inverse ratio of their turns in the coils. Okay, you know it already. Let me check if I'm recording the session or yes, I'm recording. Fine. Yeah. Moving further, you will understand that if this is true, okay, I can take I2 to this side, it becomes something like this. And for I2, I can always write this, because I2 is nothing but E2 upon the load on the right, on the secondary circuit. So if I introduce this in place of I2, okay, I know that E2 can be written as N2 or N1 times E1, and so this would be square of it times E1 and divided by R. That is there. This can further be written as N2 or N1 square times 1 over R times E1, or from here, which is equal to I1, okay? Don't forget that this is equal to I1. So I can find out how much is E1 in terms of I1, and that leads to this formula. What does this formula mean? This is E1, this is I1. So whatever is the rest there, it should be the resistance, isn't it? That should be the resistance. Yes, we call it equivalent resistance, that is seen by the generator or the primary side, supply side. So instead of R, okay, what the generator sees this as is R times square of the turns ratio. Okay, so resistance in the secondary circuit experienced by the generator or seen by the generator has changed now. And this has very important significance. This has very important meaning. I'll tell you why. But for now, just understand that the generator would produce current I1, a voltage V1, such that it is connected to a resistance which is R equivalent and not R as such before. Okay. Now, what are the consequences of this thing? The important thing that we have here is that if you change the turns ratio, you are able to change the resistance in the secondary circuit without actually changing the load. By changing simply the turns ratio, you're able to change the apparent load perceived by the supply, by the generator. Okay. Now, the important significance this thing has is that you know previously that for a maximum energy transfer, the two sides, the resistive load and the EMF device, they should have equal impedance. They should have same resistance. So if the resistance of the supply and resistance of the load, if they are same, the energy transfer would be maximum. Okay, I told you previously, if I remember, that you should try to understand this and maybe try to mathematically prove this. So I want all of you to do this. Maybe in one of the quizzes, I'll ask this question, okay? Don't be surprised, right? You should be able to mathematically prove, analytically prove that the energy transferred between source and load is maximum when the source impedance and the load impedance are equal. I'm leaving this to you as an exercise. Often this condition is not met, that's for sure. For instance, the amplifiers that we normally use with the microphones in the speakers. So amplifiers, so you've got a microphone, then there's an amplifier, and then there are speakers, isn't it? The amplifiers, they normally have higher impedance than the speakers. So you can have 8 ohms or 16 ohms amplifier here, whereas the speakers could be like 2 ohms or 4 ohms. Okay. But if this amplifier has larger impedance, then obviously it will get heated quickly and it will burn out. So you have to make sure that their impedances are matched. We normally try to match the impedance of source and load. And how we can do that? We can easily do that by connecting a small transformer between the source and the load. And by selecting appropriate turns ratio, you can change the resistance that is perceived by the source. So you can increase, you can decrease without actually changing the load. So we understand with this exercise that for an ideal transformer, the voltages are transferred in direct turns ratio. The currents are transferred from primary to secondary in the inverse ratio of the turns. The resistances or the impedances are transferred in the direct ratio squared. However, the power, volt ampere, or the frequency, it remains unchanged. It remains unchanged. And an ideal transformer does not exist. Okay? An ideal transformer does not exist. The applied voltage leads the flux by 90 degrees and induced EMF lags by 90 degrees. This is your induced flux. Sorry, this is the flux. This is the current causing it. And these are induced EMF. If you take flux as a sinusoidal wave of omega t phase, the phase of the induced voltages would lag by 90 degrees. Okay. What will be the phase of IE? With this, of course, it seems that it's going to be omega t, but it's normally slightly more than that. Oops, sorry. This is omega t plus, okay, yeah. Omega t plus alpha, yeah. All right, next. So when I say that an ideal transformer does not exist, I should also tell you what is the difference between an ideal transformer and a real transformer that you work with. So an ideal transformer should have 0 primary coil resistance, 0 secondary coil resistance, 0 reactances for primary and secondary leakages. You should have infinite magnetizing resistance, and it should also have infinite core loss resistance. Okay, but unfortunately, this does not exist. And what we have is there's some resistance which you perceive from primary circuit, the secondary circuit, where there are reactances which you cannot avoid, and they exist. Now, what's the effect of transformer losses, or especially the core losses? You've seen this before that. For the transformer core, where because of this I current in the coil, a magnetomotive force was created that would generate a flux. So the flux would always lag, okay? Initially, it was fine. Initially, it was all fine. But as cycle goes on, because we're talking of an AC current, alternating current here. And so the current becomes 0, but phi does not become 0. It becomes 0 after a certain time, okay? After a certain time, which is phase. And this difference in the phase is known as hysterectic angle. So phi is always lagging behind the excitation current. So the previous slide where you've seen that this flux and the exciting current were in the same phase is not a complete truth. In fact, they do have some phase difference, and that phase difference that the current leads the flux by some hysterectic angle, which is normally denoted by alpha. We have not considered higher order harmonics yet. We'll talk about these later, and things would still change. Any question? Okay, so we did talk about this core loss. There's another kind of loss that we have there, and it's because of the leakage flux. Of course, the core has very high permittivity or permeability, and the flux is supposed to be traveling, the entire flux is supposed to be traveling through the core, but still there's some flux that would stray out, stray away, okay? And this flux we are not able to contain. Now, the thing is, the flux which is flowing through the core has a phase difference of alpha, hysterectic angle, with IE. Why? Because it has to pass through this magnetic medium. But the flux, which is leakage flux, it goes into the air. And the air's permittivity of air is very low. It's 1. Okay, relative permittivity is 1. And so for air, if I draw this curve, how it should look like? It'll be a straight line, isn't it? For air and vacuum, it'll be a straight line like this. So what does that mean? It means that when the current I becomes 0, B also becomes 0 or phi for that matter. Okay, both the sides. So I and phi, they don't phase out. They are rather in phase, in especially in the air. So yes, IE leads phi by some hysterectic angle, but this leakage flux phi L1 remains in phase with IE. It does not lag. And this phi induces E, isn't it? Similarly, this phi L1, it will also induce an EMF, and that can be written as something like this, because this is by virtue of the leakage reactance. Okay, and that's why it has to be, because of its opposite nature, it has to be negative. And I'm introducing this J times X1 as a reactance in force coil. So this voltage, okay, if you're talking about a real transformer, not an ideal one, it has to give, it has to provide for E1, okay. So let's say if E1 is 10 and this leakage voltage induced due to leakage reactance, let's say this is 2, and then the coil, let's say the coil also has some resistance R, okay, and so there would be some drop because of this resistance of the coil. Let's say that drop is also maybe 1. So how much should be V? Should be 10 plus 2 plus this 1, isn't it? And so the generator voltage should be something that appears at the coil plus, to compensate for this voltage induced due to leakage flux, plus the drop across the primary. So if you understand this, I'll be happy and my life will be easy. Let me know if you have questions, please. So we are all on the same page. Good. Let's switch the page now. Further. So see, I was telling you that this exciting current, it has two components. One of the component produces the required flux in the core, and there's another component that has to take care of the core loss component, or the power component. It's also called the power component of IE. Okay. So, I mean, the total core loss, which is coming from the hysteresis and from the eddy currents, can be denoted something like this, and you can find out how much the core loss component of this excitation current, and so this IE has to be vector sum of IM and IC. And so that's the reason I was saying that IE is not in phase with phi. Rather, there is a phase difference, okay? But if you talk about the leakage flux, this leakage flux would be aligned, will be in phase with IE, because there it changes linearly, okay? IE and leakage flux. All right, so this flux would induce these voltages, right? And so the leakage flux should also induce this voltage. Now, this is something that appears across the primary. So if I have to add the resistive component, I mean the drop across the primary because of its resistance, and that has to be parallel to IE, isn't it? Because the drop across the resistance has to be in the direction of IE, I mean in phase with IE, because there's no reactance we're talking about. We're talking about the resistance. So it has no phase difference, zero phase. So zero phase difference, sorry. So to evaluate R1 times IE, the R1 is the resistance of the primary coil and IE is the excitation current. So I need to draw a vector of which has a magnitude equal to R1 times IE, and it should be parallel to IE here, like this. And there's another drop because of this. There's another loss because of this. That has to be at right angles to this IE, and which is this. So in short, what I'm saying is the voltage coming from the generator, okay, is a vector sum of what appears across primary. There's voltage drop on primary coil, and to compensate for this induced voltage because of leakage reactance. And so this is the total V. Oops, yeah. So you understand this now. The total V would be sum of all these three, and there's nothing new here. Yeah, it's the same thing. Now we'll see what happens when, so this is the case when there's no load connected. There's no I2 current in the secondary circuit. But now when you close this switch in the secondary side, we want to see what happens. So first we'll look at the secondary side where you have I2 current. So when the switch is closed, this current flows in the secondary circuit, which lags V2 by some angle. So let's draw this first. Okay. So this is V2, and this is I2, which lags by theta 2 degrees. Why it lags by theta 2 degrees? Because I'm considering my load to be inductive load, and so because it's an inductive load, the current would lag the voltage. Okay. Now, the voltage drop across the secondary because of its resistance will be parallel to I2. Okay. So if this is I2, in parallel to I2, this is going to be the drop of voltage because of the internal resistance of the coil in the secondary circuit. And because of this leakage flux in the secondary, they're going to be an induced EMF because of the leakage reactance. And to compensate that, this also has to be accounted. And finally, this is E2. So what I'm saying is, the E2 induced into the secondary coil is consumed by this part, and the remaining V2 would appear across the load. Okay. So what appears at the load is not same as E2. It is less than E2. And these are the two important losses that we need to consider. Fine. It's all pretty simple, but still, if you have some questions, you can ask. What I'm saying here, let me repeat again. So this E2, which is supposed to be here, okay, is not same as this V2. And okay, the V2 would be equal to E2 minus this minus this. This entire thing is called secondary leakage impedance, which can be included here. And so this is I2. Opposite to this will be your I1 dash or I1 prime. This was IE with the hysterectic angle. And some of these two is this I1, which is primary current. And this is the voltage coming from the supply. This is power factor of the load. This is power factor of the supply. Yeah. Yes, please. Any question on this so far? Good. Now, when you go to purchase a transformer, the transformer would have a plate which reads these kind of things. So it will tell you it's a 20 kVA transformer with 3300 and 220 volt ratings on the primary, on the secondary, or high voltage side, low voltage side, and the frequency. Okay. So this ought to be the rated power output of the transformer that you would receive at the secondary. You should know what is the difference between kVA and kW, kilowatt. So when you consider for kilowatt, the power factor is 1, and the power factor is not 1, we call kVA. So kVA times the power factor would be equal to kW. Okay? So kW is a unit of real power, whereas kilowatt ampere is a unit of apparent power, which includes real and the reactive power. When power factor is 1, both kVA and kW would be the same. Otherwise, they are not the same. You should know where does this reactive power comes from and what is significance. I leave this to you for your own practice and exercise. Now, the rated output is limited because heating losses and other core losses. Now, if you talk about the losses in transformer, you have two kinds of losses. One is the core loss, or we also call it iron loss. Okay, it's to make it more specific. We call it iron loss, and this ohmic loss we normally term them as copper loss. Okay. So you got iron loss and copper loss, or you got core losses and ohmic losses. While the core losses, they depend on V. We've seen the empirical formula last time. The core loss depends on voltage, the ohmic loss depends on current. The core losses, they are not affected by the load power factor. So the load power factor could be anything or everything. The core losses, because they only depend on the frequency and the voltage, they are not affected by the load power factor. Okay. This rated primary and secondary voltages, they depend on whether it is a step up or a step down. So if you flip your transformer, it will change. Okay. There is something called rated output from transformer. Okay. It is expressed in terms of kVA, not kW. See? Why? Because the power factor of current is decided by the load connected. Okay. And so it's going to be changed. It's going to change. Now, to find the rated primary and secondary currents, all you need to do is, this is for primary, use these two, and you find out this is the rated current in the primary circuit for the full load, of course. And for secondary circuit, the rated current would be found by dividing the power rating to the voltage. So far, so good. Now we'll talk about how to draw an equivalent circuit of a transformer, because when I'm trying to study the transformer, if I have to use it in simulations, which you would see in this current lab exercise. So to simulate the transformer, I need to come up with an equivalent circuit of the transformer, and then I can do many manipulations. Okay. So for that, we draw such kind of a circuit where we don't show many things. Okay. We use all these combinations, and using circuit theory, you can analyze it. See, this R1 and X1, it comes from the primary coil. These are the leakage impedances. So this is leakage resistance, leakage reactance of primary and secondary. Number of turns, voltages, okay, and the currents. These are shown like this. So this is an example of an equivalent circuit, but this is not the correct impedance, the current equivalent circuit. The correct one would be something. Okay, I'm not showing it anyways. So for the current, what we normally do is we don't show up these things. So yeah, let me go to the next slide and then show it. So this is there's an equivalent circuit of a transformer, which we call an exact equivalence. So we are not missing on anything. We have everything there. Okay. And if we make some assumptions and if we miss something, then the equivalent circuit would be an approximate equivalent circuit. So this is an exact equivalent circuit where you have leakage impedances, currents, primary current. Okay. Now, part of primary current works as an excitation current, and the other one goes to compensate for I2, right? And the one that goes for excitation, part of it would create the flux, and the other part counters the core losses, which are pretty high. Okay. And the magnetizing current, it kind of is for this magnetizing reactance. In the secondary circuit, this is the load voltage, leakage resistance and reactances, leakage impedance, voltage induced. Now the primary current, as I was saying, it has two components. Okay, this current has two components. The load component to counteract secondary MMF, which is this. And there's another component, which is exciting current, and it consists of the core part and a magnetizing part. This core component of the excitation current is in phase with V1, with the induced voltage here, and it gives core loss. Okay, so if you multiply these two, that will give you core loss. I mean, to find RC, what you can do is you can divide V1 prime with IC, you get this core loss. Yeah, I mean, core loss resistance equal to core loss. And IM, which I'm talking about here, the magnetization current, it would lag by 90 degrees test through produce the flux. And it is shown by the reactance XM, defined something like this. Okay. Now this is an example of an equivalent circuit for a transformer. I've told you why we need it. But then if I'm working, let's say on the primary side, then how do I connect these quantities together? How do I connect them? because it seems like they are not connected. There's no circuit. And to apply a circuit principles, it's a bit difficult. So what we do normally is we transfer all these quantities from secondary circuit to the primary circuit. Or if I'm working on the load side and doing some calculations, I can actually transfer all the primary side values, okay, towards the secondary side and make just one circuit. And I'm allowed to do this because I know that if I'm taking secondary quantities to the primary side, so the secondary quantities referred to the primary side would be something like this. The resistances and impedances would be multiplied by square of the turns ratio. The currents would be multiplied by the inverse ratio of the turns. The voltage would be multiplied by the direct ratio of turns. Okay, and then I'm able to transfer, because what this primary circuit sees this as, or this as, I know how it looks like. I know how it will look like if it is brought to the primary circuit, or how it will be perceived by the generator or the supply on the primary side. So let's see, and let's do it. So here, what I'm doing is, I've transferred all the secondary quantities to the primary side. And so R1 and X1 would remain the same, but R2 would become R2 prime, which is this. I1 stays the same, but I2 would become something like this. E1 remains the same, but E2 would become something like this. B2, it would become, this is how it will take the new values. Okay. And as you can see, we have not overruled any of these laws. That this is something that we have derived before. It's just that the quantities have been transferred from the secondary to the primary. And you can do vice versa. You can also take the primary quantities to the secondary side, and then it would look like something this. So there's no quantities on the primary, everything is on the secondary now. So R1 has become this now. I2 has become, I1 has become this. V1 has become this. E1 has become this. Why do we do this? Is that so that we can use our methods that we have for circuit analysis, and we can use those methods here and solve for the circuit parameters. But this still looks quite complicated, and I can further simplify it. So there are few ways by which you can simplify this equivalent circuit, and you need to make certain assumptions. The assumptions that you normally make would be something like this. So for instance, what I can do is, this is the general form of equivalent circuit where I've got rid of those coils and everything. So I've connected everything here. Okay. Compared to the one that you saw previously, I'm taking these two primary and secondary coils away, and it looks something like this. Okay. The ideal transformer is not shown in here. That's it. You can also draw a phasor for the equivalent circuit. Like if you have transferred all the secondary quantities to the primary side, and so starting from this Im and phi, and then this is IE, and then you've got I1, I2, that's fine. And then on top of and then you got V2, which is this I2. And V2 would be the voltage appearing on the load side. And if you add loss on the drop on the secondary coil and the leakage reactance, considering that, it becomes E2, and further adding the primary components, it becomes V1. So this is how you can actually draw phasor for the equivalent circuit also, where you transfer all the quantities from secondary to the primary side. Or you could do it upside down to look like a phasor for an equivalent circuit, that for where you have transfer all the primary quantities to the secondary side. See, I was talking about those approximate equivalent circuits. So these are the cases. I got these 4 cases to explain to you, and then rest you would understand yourself. So in the first case, you know how it was a bit difficult to solve those 2 parallel circuits. So what you can do is, you can shift this central arm, the shunt branch, on the left hand side, and bring the resistances and reactances together. So this helps me in easily connecting or adding up the resistance and the reactances, right? But this is not correct. This is not accurate. I mean, this will not lead to an accurate analysis. But the fact is that this being very small, okay, what I'm losing on here is I1 times R1, okay? So if it is too small to be neglected compared to this IE, I can actually neglect it, and I can shift this side. So I can consider that I2 passes through R1 and X1 also. Okay. So this kind of approximation can be done both ways. Like, you can shift your shunt arm on the left hand side, or you can shift it on the right hand side. Here, I1 was not flowing through R1 and X1, and here in this case, I1 is flowing through R2 and X2 as well, and that's the only difference. Okay, you can actually remove the entire shunt branch. Okay, you can actually remove it if your systems are more than 100 kVA. Okay, because in that case, this equivalent reactance is pretty larger. This reactance becomes quite higher than this. Okay, for transformers which are more than 100 kVA, the value of reactance, rather equivalent leakage reactance I'm talking about here, is pretty high. Okay, so that you can neglect this. Neglecting this means you can just ignore this. IE would be too small. IE would be too small to be considered in front of I2, and so you can ignore it. For systems which are more than 500 kVA, we can even ignore the entire of this internal resistance, and we only consider the leakage reactances, which are pretty high. Okay, let me not bore you further. Let's do some analytics now. What about the power loss? Let's calculate the total copper loss or the ohmic loss. So you have primary and the secondary coils, and okay, good. So I1 and R1 flowing in, I1 current flowing in primary circuit, I2 current in the secondary circuit, and this is how the total ohmic loss or the copper loss can be commensurated, can be calculated. Okay. Now I can express in I2 in terms of I1. How I can do that? In place of I2, I can write I1 times N1 into N1 divided by N2. And if I do so, see, this remains unchanged. Here for I2, I'm replacing it with I1 times N1 by N2. And if you further solve it, it comes out to be, you take this outside common, okay? And so what is this? This is nothing but R equivalent, isn't it? R equivalent on the primary side. So if you take R2 from secondary to primary side, it would be something like this, isn't it? So the total ohmic loss, it would become I1 square, which is the current in the primary circuit, times the equivalent resistance of the entire circuit as if the secondary resistance has been transferred to the primary. Or let's not do this, do it other way. Now let's convert this I1 to I2 times N2 over N1. And then try to solve it, okay? When you solve it, it turns out that the total ohmic loss would be current in the secondary circuit square root of the current in the secondary circuit, times R equivalent in the secondary side, which is R of the secondary side plus equivalent resistance of the primary side when it is transferred to the secondary side. We call it, in general, the total ohmic loss would be current on that side squared times equivalent resistance referred to either side. It could be the primary side or it could be the secondary side. Simple. Now let's try and test how much have we understood, okay? And for that, let's solve an example. Now, for instance, we have given a transformer 33 kV, and the ratings are given for the primary and secondary, 50 Hertz, single phase transformer. The resistance of the primary coil is 2.4, secondary is 0.03 ohms. The leakage reactances are 6 and 0.07. Now you need to find the primary resistances and reactances refer to the secondary. So we want to take primary R and X refer to the secondary. And then we also want to see what happens when you refer the secondary R and X to primary. Okay. So the primary resistance refer to the secondary would be R1 times N2 or N1 square. And so from 2.4, it'll become 0.024. Okay, 100th, because the ratio is 100. Turns ratio is 1/10, and square root of that would be 1/100. Likewise, the leakage reactance from 6, it will become 0.06. Now, if you bring quantities from the secondary to the primary, so this 0.03 would become 3, and 0.07, it would become 7. Now, if I ask you to find the equivalent resistance, it's pretty simple, isn't it? All you need to do is add the resistance on the primary side, and if it is referred to the secondary side, so leakage, the equivalent resistance referred to the primary. So 2.4 was already there, and then when this is referred to primary, it becomes 3, so the total would be 5.4. Similarly, for the reactances, 6 was already there, and when it is referred to the primary, it becomes 7, so it will be 13. Oh, sorry, secondary side. Okay. So leakage reactance, yeah, fine. So this is the case when they're referred to the primary and they're referred to the secondary. So let me clear all. When the quantity is referred to the secondary, this is already there, and this will add up now. 0.024 would make it 0.054. And when this is referred to here, it will become 0.13. Okay. And then we also have been asked for like total ohmic loss. So we know the formula. That's if you're considering on the primary side, then it's going to be I squared, which is this rated current on the primary circuit, square times equivalent resistance on the primary side. But if you're interested on the secondary side, so the current the secondary side is 150 square times total resistance on the secondary side. So total resistance on the secondary side would be this plus 0.024. So that makes it 0.054. So the eventually ohmic loss turns out to be the same in both the cases. Questions, please. We have some more time. So let me move on. Now in the same question, if I ask you to find what is the voltage to be applied the high voltage side for a short circuit current of 160 amps in the low voltage. So here you want 160 amps in the low voltage side. Okay. So if I bring that 160 amps in the primary circuit, okay, 160 would become 16 amps. Okay. Currents are converted in the inverse of their turns ratio when they're coming from the second primary. That will be divided by 10. Fine. And the equivalent resistance is, this is 2 plus, now it will become 3. This will become 6 plus 7, 13. And this is 16 amps. It's quite simple in that case, isn't it? All you need to do is, so this is the impedance, as you can see. Okay, you know the impedance, which is this. We need to find the voltage and how much is the current? Current is 16 amps. Okay, 16 amps current, and this is the total impedance. You need this much of voltage. And if you're asked to find the power, so the power input is going to be I squared times total equivalent resistance of the primary, which is this. Or the power input is VI cos theta. So this is V, this is I, and cosine of theta is this. Because I know this over this would be the cosine theta. I mean, this is basically Z cos theta. So yeah, it comes out to be the same. No questions? Okay. There's another such kind of a transformer. It's a 10 kVA now. And the ratings have been given to us. We know these. Later, I'll tell you how to find these. Okay. So far, we've been just using these parameters, but then we'll do certain tests on transformers to see how R1 and X1 and R2 and X2 can actually be found through an experiment. Find the secondary voltage, whereas the primary is constant at 2500. Okay. So, first case, when the low voltage side is connected to the load impedance of this. So, the low voltage has been connected with this load, and we need to, so this is the low side voltage. Now, because we are talking about the load and need to do all the calculations on the load side, how about bringing all the primary side parameters to the load side now? So refer all the primary quantities to the secondary side, and that case, R equivalent would be, see, okay, yeah, we have this already, 0.048, and this another 4.8 coming to the secondary will become 0.048. Okay, and so the total would be 0.096. Similarly is the case with the reactants. 0.112 and 0.112 will become 0.224. We know the impedance, and then all you need to do is divide the voltage with the impedance to get the current. And once you know the current, you can easily find out the voltage across the load, which comes out to be 242. This you could have done using a phasor diagram also. Okay, using a phasor, it's easy. I mean, you can do it, and it depends. You can either use a phasor to solve this problem, or you can do it analytically. Okay. So with this, I would close the session. If you have any question, you can ask me, and I'll stop recording now.